we move on to applying this to simple problems. Let's do this problem. You remember one of you asked in the first module, how do you deal with non-prismatic beams? Well, if your beam is tapered, you can't do this. Your beam has to be piecewise prismatic, then only the slope deflection method can be used. So here you have a beam where one half of the beam has a higher EY value, 2 EI, and the other half is only 1 EI. And I have given you 3 loads, one UDL, one load exactly at B, and one load in the middle of AB. Okay. How do you solve this problem? Well, let's proceed slowly. This has an unknown deflection. It's when we say sway, normally we think that sway is always horizontal, not necessary. You have a vertical sway here, right? So you have a deflection at B and you have a rotation at B, and they are your unknowns. You don't have a deflection or rotation at A and C. You've got 2 unknowns. You need 2 equilibrium equations. Okay. Now let me go back to you and ask you, okay, one equilibrium equation, okay, tell me both the equilibrium equations corresponding to theta B. Let's go back to the audience. It's the same answer that you gave me earlier, so let's not waste time. MBA plus MBC is 0. What's the second equilibrium equation corresponding to delta B? Anybody? At least give me the concept. You must give me an equation which will involve MAB, MBA, MBC, MCB. What is that equation? I'll give you a clue. You have to separate out the 2 free bodies. I'll draw it for you. I've drawn it for you. Now tell me what to do. You have to have a logic. Now look at this. I've separated out the 2 beams. I've marked the shear forces VAB, VBA, VBC, VCB. Now using these terms, can you tell me what the answer is? Anybody? Ah, very good, very good. VBA plus VBC equal to VB, but which load is VB? What is VB? You're right. You have to just finish it, score the goal. What is VB? Is it plus 40 or is it minus 40? You see, if you join these 2 elements, you will get VBA plus VBC. It's pointing upward. So you must have a net load acting upward, but you have a net load acting downward. So it's not plus 40, it's minus 40. These are the mistakes you can make. You remember that why are moments equal and opposite at a beam junction? Because when you join the 2 beams, there's no net moment there. If you join them, the net moment will be the net moment that you get if they were not equal with the same direction. So don't reverse it. So VBA plus VBC is equal to VB pointing upward. There must be a net load pointing upward equal to VB. If your net load is pointing downward, as in this case, then it should be minus of that load. That's why it should be minus 40. Okay. Then you can express VBA and VBC in terms of MAB, MBC and so on. We'll do that later. I hope this is clear. It's very, very, that's why sway type of moments, I think we know how to do that. MFAB, MFBA, WL by 8. MFBC is minus Q naught L squared by 12. MFCB is the same thing plus. You can summarize your friction moments. Then we write down the slope deflection equations. Mechanically you can do that. You have to write the correct chord rotation. Chord rotation is delta B by 10. Phi AB is delta B by 10. It's plus because it's a clockwise chord rotation, assuming delta downward positive. And so you can write MAB. Now what do you normally write? MAB is equal to MFAB plus 4 EI by L into theta A. Theta A is 0 here. You need not write that part. Plus 2 EI, here you have 2 EI by L into theta B, then minus 6 into 2 EI by L into Chord rotation. Chord rotation is delta B by 10. You have to be clever to write this. MAB is this. MBA is the same thing, except you write MFBA and you write 4 into 2 EI by L into theta B. Similarly, you write for MB for the beam BC. For beam BC, the chord rotation is negative. Please note. The chord rotation is anti-clockwise and it's delta B by the span, which is 10. So this is what you will get. Okay, the signs are very, very important. MFBC is 4 EI by L into theta B plus 2 EI by L into theta C, but theta C is 0. Okay, this should be theta C on top into chord and minus 6 EI by L into the chord rotation. Similarly for MCB, you've got your slope deflection equations. You can expand them out and you can write them in matrix form like this. Okay, look at this. If you know EI theta B and you know EI delta B, you know the solutions. The first column that you have are your fixed end moments, these are your stiffness relations, and you can go ahead and solve this. Equilibrium equations conceptually we wrote. For theta B it's MBA plus MBC equal to 0. For delta B we said it's VBA plus VBC equal to minus 40. Remember? Now what is VBA? Well, you have to look at that free body and correctly write the value for VBA. VBA, look at this. This 100 kilonewton will be shared equally by VAB and VBA. So 50 will go there, that's 50. Then the additional share you will get is MBA minus or plus MAB divided by 10. So MAB plus MBA by 10. Here this 10 kilonewton meter into 10 meters is 100 kilonewton. Half of it will go to VBC. That's how you get 50. And then these clockwise moments will increase the shear on the right side and reduce the shear on the left side. So you get a minus of MBC plus MCB by 10. So this is a problem which really tests you. You can't do it blindly. You have to understand the physics behind it. You must get the signs correctly, and that's a huge challenge. You saw earlier how easy it was to make the mistake of not putting minus 40. Now here also you have to be very careful. If you write them correctly, you can't go wrong. You've got your two equilibrium equations, tell you something very important. These are matrices which have a lot of meaning. This matrix here is actually a property of the structure. It's called a stiffness matrix. Okay, I want you to understand this because the next advanced topic is matrix methods. So let's physically understand that by going to the board. So this is the structure we have. The span here is 10 meters. This is also 10 meters. This is 2 EI. This is EI. This is A. This is B. This is C. We are choosing our coordinates as 1 and 2. So this rotation here clockwise, theta B is D1. D1 is theta B. And by definition, if D1 is theta B, then a moment applied at this joint F1 is also going to be clockwise positive. That's the definition. And if this deflection here downwards is D2, then F2 will be a force acting there, and the stiffness relationship is very simple. F1, which has a units of kilonewton meter, and F2 is equal to K11, K12, K21, K22 into a displacement vector which is D1 theta B and D2 delta B. Theta B is clockwise positive, F1 is clockwise positive, theta is downward positive, F2 is downward positive. This matrix is called a stiffness matrix. It's a very powerful matrix. It's a property of the structure. which means if I want to find D1 and D2 for any combination of F1 and F2, I just have to invert this matrix for any combination. Now, in the slope deflection method, accidentally you are ending up with the stiffness matrix when you write down the equilibrium equation. We can actually derive this stiffness matrix from first principles. And why don't we do that? So, how do you get this matrix? If you take the first column of this matrix, you would get them if you were to put D1 equal to 1 and D2 equal to 0. Let's do that. Let's apply D1 equal to 1 and D2 equal to 0. Then clearly F1 will be K11 and F2 will be K12. That's it. If you want to get these two, then you apply D1 equal to 0 and D2 equal to 1. Here you have only two coordinates, but in a big multi-storied frame you can have 100 coordinates, 100 by 100 stiffness matrix. You will find that the stiffness matrix is symmetric. K12, take the same structure, physically see what it means to get a shape like that. We are now saying we are arresting the D2. D2 means this should not go down. How do you arrest it? Well, give it a support. Of course, it's an artificial imaginary support. And then we want D1 to be unity. So let's do that and you will get a deflected shape which is going to be like that. Right? And this is D1 equal to unity and D2 is 0. Got it? Now, you can either arrest both degrees of freedom and consider rotational slip or deliberately give an external moment here. This moment that you give externally is called K11. So that's F1. And whatever reaction you get here in this imaginary support pointing downwards must be by definition K21. Can we derive this? Why not? So if you separate out these two elements, you can have one beam here with 2 EI and span of 10 meters. And the other beam here with just EI and span of 10 meters. Let's apply a moment here and get it to rotate like this so that the slope here is 1. Apply another moment here, get it to rotate so that the slope here is also 1. Obviously, when I do this, the moment that I need to apply here will be 4 EI by L. We know that. L here is 10. So let me put 10 meters. And you will get a carryover moment here, which is 2 EI by 10. And this will give me reactions, right? This will be 4 plus 2, that will be 6 EI by 10 squared. Here I get the same thing, only thing here it's 2 EI, so it will be 4 into 2 EI by 10, and I get a carryover moment here 2 into 2 EI by 10, and I get a reaction upward here and downward here. The reaction that I get here will be 6 into 2 EI by 10 squared. With this understanding, K11 is going to be this plus this. So that is 12 EI by 10, which turns out to be 1.2 EI. and K21 is going to be the sum of these two, and K21 should be pointing downward, so it should be, which is minus 0.06 EI. Isn't that what you got? And you could get a question, derive a stiffness matrix for this. You can do it effortlessly. That's why the stiffness method is very powerful, because if you write a software, the computer stores the stiffness matrix of the complicated structure and it says, give me any loading you want, I can find the unknowns without solving any slope deflection equation. You get the same answer. So to understand stiffness method, you have to understand slope deflection equation. After that, it's very simple, theta b and ei delta b, and you can get free body diagrams, many moment diagrams. Okay, very interesting problem, not usually discussed in textbooks, but it clarifies. Let's do another problem. This is a simple problem. Here, what's the degree of indeterminacy? Well, let's say you have theta b, theta c you can ignore, you have delta bc, right? Your fixed moments are 0 here. This is a simple problem. You can write down your slope deflection equations. For AB, you will write minus 6EI by phi. Phi is delta B by 4, delta B or delta BC. You should write delta BC ideally. And for MBA, it is minus 6EI by 4 by L into phi. And for BC, BC is not affected by sway, it's only affected by rotation. You should use this equation. If you simplify, you get something like this, very simple. Now, equilibrium equation, okay, you know this adds up to MBA plus MBC will now add up to plus 50. Why does it add up to plus 50? Because when you join them, though both are clockwise, you will get net something which is also clockwise, it should be plus 50. That's the reason you are putting plus 50, not minus 50. See, there is a difference between an equilibriant and a resultant. This is a resultant. Equilibriant will have an opposite sign, but a resultant will have the same sign. So this is a resultant. For delta BC, I am not going to ask you, you should know by now. Delta BC, the equation is sigma fx equal to 0, which means HA will be 0, which means if you take the free body, MAB plus MBA by the height is 0. That's it. 2 equations, solve them, get your answers, plug them back into the slope deflection equations, and draw your free body. Now, I am going to give you a shortcut. Okay, it's a very beautiful shortcut. What is the shortcut? The shortcut is you can ignore sway. How do you ignore sway? Well, let's say you can ignore it. Take my word for it and let's proceed. That means not only I am going to ignore theta c, I am going to ignore delta bc also. Okay, so my unknown displacements are actually only theta b, one unknown, MBA and MBC. MBC will obviously be 50 minus MBA. There's only my moment unknowns, and MAB will be equal to minus MBA because there's no other load. So it's a very straightforward problem. And what is my primary structure if I choose only theta b as my unknown? That means I'm not going to stop theta c, I'm not going to arrest delta bc. So my primary structure is a structure where theta b is fixed against rotation, but it can sway. I'm putting a guided fixed support like this at B, and here I'm fixing this. It doesn't matter if this sways or not, right? These are my free bodies. So what are my fixed moments? Fixed moments are 0. There is no load. Let's proceed and do this problem, but before that, let's go back to what happens when you deal with a guided fixed support. You remember we did this we got the simplified slope deflection equations when you have guided fixed support. MAB is MFAB plus EI by L into theta A, and MBA is MFBA minus EI by L into theta A. How do you get minus and plus? Because look at this deflected shape. Okay, this is like a cantilever with a load pushing it down. You get a similar shape, but you can see there are sagging moments, and this will be clockwise. That's why MAB is plus. This will be anti-clockwise, and the stiffness is EI by L. Clear? What happens when you have a guided fixed support at A? Then you get a picture like this. Now theta B is the rotation that you are applying. You will find that the equations will change slightly. Why? Because you have an anti-clockwise moment at A and you have a clockwise moment at B. So you should always have this feeling when you write these equations. So it's MAB is in this case MFAB minus EI by L into theta B, and MBA is MFBA plus EI by L into theta B. With this background, let's go to this problem. Okay, we are saying we are going to ignore the sway degree of freedom, and then let's see what's happening. When you write the slope deflection equations, you've got a guided fixed support at B for the element AB. Imagine you're applying a rotation theta B. Can you not see that you have clockwise rotation at BA and anti-clockwise at AB? That's why you will write here MFAB minus EI by L. L here is the height 4. That's the reason. And for MBA, you will write plus. Don't make a mistake here. So for multi-storied frames, we are going to look at that. This is what you should mechanically write. Then for MBC, it is MF naught BC plus 3 EI by L into theta B. Here EI is EI in this problem. Expand it. Equilibrium equations. You have only one unknown now. See, we've got rid of delta BC. Theta B alone is your unknown, and MBA plus MBC must add up to plus 50. Substitute. You got an answer. Plug in those values. You get the same answers you got the hard way treating delta. The harder way is treating theta C also is unknown. That is the standard textbook solution. In this problem, in a standard textbook will require, now we are using only E as an unknown. It's a very powerful way of solving the same problem. You can draw your free bodies, draw